Hello, we're group number 10 and here we are presenting the results obtained in the project of the experimentation of a shell and tube heat exchanger. First, we have the objective of the entire project, then some important concepts and introduction in order to a better understanding. After that, materials and methods, later, the results, and finally, analysis and comparison, so as the conclusions. The main objective of the project is to characterize a shell and tubes exchanger in order to determine the overall heat transfer coefficient for the countercurrent and parallel flow. In order to completely understand these results, we need to talk about some important concepts first. Overall heat transfer coefficient is a measure that represents the total resistance of heat transfer from one fluid to another. The effectiveness NTU and log mean temperature differences LMTD are two solution methods that approach heat exchanger analysis from different angles. Both methods share common parameters and concepts and will arrive at the same solution to heat exchanger thermal capacity. During the experimentation, we analyzed both of the heat exchanger arrangements. In the countercurrent flow, cold and hot fluids go on opposite directions, while in the parallel flow, both go in the same direction. Based on the experimental results, calculations were made by the NTU and LMTD methods, as we can see here their main equations. We also calculated dimensionless numbers for the shell and tubes, such as Reynolds number, Prandtl number, and nozzle number, as well as the pressure drops for the tubes and shell. For the theoretical calculations of the overall heat transfer coefficient, the general resistance equation was used in order to solve it to find the shell and tube side transfer coefficients. Two methods were used. On one hand, the KAKAK method for the shell side coefficient with the Bell-Delaware correlation, and for the tube side transfer coefficient, the Petukov-Kirillov-Nutzel correlation. On the other hand, the second method was based on current correlations, for tube and shell side coefficients were applied, where this is the equation for the tube side and this is the equation for the shell side, where JH value is found plotted on Kern's book and his solver. After this, the respective method coefficients were applied in the general resistance equation for the results to be compared regarding each method. The correlation for the stainless steel was used to calculate the resistance of the alloy based on the composition of each of the components on this. Here, we can see the results found after doing the calculations. As it can be seen on this table of experimental results of the overall heat transfer coefficient, there is not much difference between values in both methods for the countercurrent flow, as it was expected, but not for the parallel flow. Pressure drops are almost the same in both flows for the tubes, but not for the shell, which is bigger for the countercurrent flow. Now, the theoretical overall heat transfer coefficient calculated with KAKAK and Kern methods show a significant difference on its values. It can be applied to the fact that both calculation methods are very different and include different variables, as well as correlations and corrections that change drastically the results of the calculations. Here we can see the results of the parallel flow, and here the ones for the countercurrent flow. Experimental polynomial curves were built with experimental values by making an adjustment in function of temperature with regard of different variables such as density, specific heat, also conductivity and viscosity in order to model these variables needed to do calculations at any temperature. With all the results obtained, we can observe that experimental results compared with the theoretical ones have higher values of the overall heat transfer coefficient. The error rate for both flow arrangements is between 40 and 60%. This might be due to the several factors. First of all, the experimental setup affected the accuracy of the data, especially because of the air bubbles found during experimentation that makes heat transfer more difficult. The difference between experimental and theoretical calculations procedures is the main factor that affects the results. On the other hand, methods proposed by Kakak and Kern considers heat losses and in the tube bank, correction factors and bagel cut and spacing, baffle leakage and bundle bypassing effects due to clearance between tubes and variable baffle spacing and materials. Since these factors that multiply the result are under the value of 1, the global heat transfer coefficients are lower with the Bell-Delaware correlation, as well as Petrikov-Kirillov equation does corrections in terms of the material properties that change with temperature and expresses dimensionless numbers coefficients for experimental data approximations to reality. Furthermore, the CACAC equations part from experimental data polynomials and consider temperature effects on dimensionless numbers, as well as the thermodynamic properties in correction coefficients. When it comes to comparing the different flow arrangement, parallel and counterflow, it is evident that experimentally and theoretically the results for all the variables obtained are not extremely different from one another. There are some important differences that should be highlighted, such as the fact that with all parallel flow arrangement, the heat transfer is more efficient than with a countercurrent flow arrangement. It is also important to observe that the pressure drop in shell and tubes is lower when the fluids flow parallel. The pressure drop in the shell and tubes can be considered negligible since the losses are 1 to 5% in the corresponding diameters. As conclusions, we can see all the results obtained, and it can be said that errors found in these values can be attributed to the experimental setup, also to the air bubbles found that make more difficult the heat transfer, and finally, because of all the assumptions made in both calculation methods.